Have you ever seen those tiny little numbers floating next to bigger ones in math and just kind of wondered, what are they all about? Well, today, we're on a mission. We're going to treat exponents like a secret mathematical code, and by the end of this, we are going to crack it wide open together. So, let's get right into it.
So let's start with the most fundamental question, right? You've got your big number, the base, and then this little number hanging out up to the right, the exponent. It might look small, but it's packing some serious power. So what is its job? What is it actually telling us to do? And here it is, the very first key to our code. An exponent is really just an instruction. It tells you exactly how many times to take that base number and multiply it by itself. It's basically a shortcut for repeated multiplication. Think of the exponent as the director and the base number as the star of the show. And this makes that whole abstract idea super clear. When you see 2 to the power of 3, it does not mean 2 times 3. Nope, it means you take the base, which is 2, and you multiply it by itself 3 times. So 2 times 2 is 4, and 4 times 2 is 8. Simple as that.
All right, so we've got the basics down. But you know, every good code has a few twists and turns. Let's see what happens when we start throwing negative numbers into the mix. This is where it starts to get really interesting.
So the whole game here comes down to one thing. Is the exponent even or odd? If it's an even number, 2, 4, 6, those negative signs inside the parentheses are going to pair up and cancel each other out, leaving you with a positive result. So -3 times -3 is +9. But if that exponent is an odd number, you're always going to have one negative left over without a partner, which makes the whole answer negative. Okay, now this is a classic math trap, so you've got to watch out for it. Those parentheses, they are everything. In that first example, -3 squared, you're squaring the whole thing, the entire -3. But without those parentheses, like in -3 squared, the order of operations totally takes over. You have to square the 3 first, which gives you 9, and then you stick the negative sign on it. It's such a tiny detail, but wow, it makes a huge difference in your answer.
So we've wrestled with positive and negative bases. Now let's look at something that might seem a little weird at first, but once you see the pattern, it's perfectly logical. It's time to decode the power of 0.
Check this out, it's all about the pattern. We start with 3 to the third power, that's 27. When we drop the exponent down by 1 to 2, the answer is 9. What just happened? Well, we divided by 3. Let's do it again. Drop it to the power of 1, the answer is 3. Yep, we divided by 3 again. You see where this is going, right?
Okay, so if we just follow that logic one more step, if we decrease that exponent from 1 down to 0, what do we have to do to our last result, which was 3? What's the next logical step in this sequence?
Exactly. You just divide by 3 one last time, and 3 divided by 3 is 1. This is a golden rule of the code we're cracking. As long as the base isn't 0, anything to the power of 0 is always 1.
So why stop at 0? I mean, the pattern doesn't just hit a brick wall. Actually, it keeps right on going, and it leads us directly into the world of negative exponents. This is where the code really starts to open up some cool possibilities.
That pattern of dividing by 3 just continues. So we're at 3 to the power of 0, which is 1. If we decrease the exponent again down to -1, we just do the same thing. We divide by 3. And what's 1 divided by 3? It's 1/3. Go to -2, you just divide by 3 again, and you get 1/9.
So a negative exponent isn't about making a number negative. Not at all. It's really just an instruction. The easiest way to think about it is that the negative sign is telling you to flip the base to the other side of the fraction line. That's its whole job. Once you flip it, the exponent becomes positive and you can solve it.
Let's actually watch that flip happen. 3 to the power of -2 doesn't become -9. Instead, that little negative exponent tells the 3 squared to move downstairs into the denominator of a fraction. That leaves a 1 on top, and since we all know 3 squared is 9, our final answer is 1/9, which is exactly what our pattern told us it would be.
Okay, team, we have done the hard work. We've deciphered the rules for negative bases, for the power of 0, and for negative exponents. We basically have all the keys to the code now, so let's put them to work.
So when you're faced with a problem that looks complicated, just remember this simple 3-step mission. Step 1, substitute. Just plug in the numbers where the letters are. Step 2, exponents. You gotta handle those little guys first, they get top priority. And finally, step 3, operations. Just clean it all up with the final addition or subtraction.
All right, let's walk through this one together. We need to solve a squared plus c cubed, and we know that a is 3 and c is 2. So step 1, substitute. We'll swap out those letters for their numbers. That gives us 3 squared plus 2 cubed. Now, for step 2, we take care of the exponents. 3 squared is 9, 2 cubed is 8. And for our last step, the operation, we just add them together. 9 plus 8 gives us our clean, final answer of 17. See? When you just follow the rules of the code, it leads you straight to the solution.
So think about this for a second. We've seen how exponents can make a small number like 2 explode into 8. And we've also seen how a negative exponent can shrink a number like 3 all the way down to 1/9. We know they can make numbers huge, and they can also make them incredibly small. But that just leaves one final thought. What if an exponent wasn't a whole number at all? What would a power of 1/2 even mean? That sounds like a code for another day.